Recall that how far left the poles are in the left half plane tells you how fast that exponential envelope is going to decay, whether it's on the real line or not. Further to the left, in the left half plane, the faster the decay. So if you had a system with multiple poles, which pole would you say dominates? Because poles further left shrink quickest. Their effects disappear quickly compared to the ones more right in that complex plane. So the dominant pole or pair of poles would be the rightmost poles in the complex plane. And we'll see how we can approximate more complicated systems with prototype systems by using the dominant pole concept. Here, we already went through a bunch of how to sort of translate pole locations for a prototype system to time domain specs. What if you don't have a prototype system? Well, there you might be able to get away with the concept of dominant poles. You can either simplify your model of the system by modeling only using the dominant poles, or you could describe the behavior or specify the behavior you want by where the dominant poles are, even though it's a more complicated system with more poles and more zeros. So we'll get into that and see how good it is. And here's the calculations. You start out with the original transfer function. You approximate it. If the rightmost pole is a real pole on the real line, you approximate it with a prototype first order system. Sigma over S plus sigma, that part, its final value to a step input is 1. So if your original function had a different final value to a step input, you need to scale it so they both have the same final value. Similarly, if your rightmost poles are a complex pair, you would approximate it with a prototype second order system scaled by that final value to a step input. Let's see how that works. First, let's just look at examples. Here is a repeat of formulas I just gave you. Here's an example. This is a second order system, but it has 2 real poles. So it's overdamped. You have a pole at -2 and -10, so the dominant pole is -2. So here is that approximating transfer function. Here it is simplified. Here you have a third order system that's least factored for us. This one has complex conjugate pair of poles. As this pole is on the real line. This pair of poles is at -2 to the left, and this one's at -10. So the dominant pole is the complex pair of poles. And here's how you'd approximate it using this formula up here. How well does all that work? Well, I won't go through all the arithmetic, but say this was that same original function. It's second order, but it has 2 real poles. Here's its step response. Here's the approximating function, which is a first order system. We're approximating a second order system with a first order system. Here's its step response, and here's the plot of it. We call that a pretty good match. There's a lot of approximation in classic control systems. We consider that a pretty good match. Let's make a note of this. This guy's poles were at -2 and -20. That's a factor of 5. Non-dominant pole is 5 times to the left on the real line as the dominant pole. I'm not going to go through all this arithmetic, but the difference between the approximating function and the original function in terms of its step response is this, which means the bigger B is compared to A, the smaller your error is going to be. Let's look at that. Well, let's look at another example and see how much it hurts us. Here's another second order example, but two real poles. Poles are -2 and -3, so the poles are much closer together. That ratio is only 1.5. Previous example, it was 5. And here's a plot of the two responses. Not quite as good a match. Depends on how well you want to match, but it's certainly not as good as the other one. So factor of 5 is pretty good. A factor of 1.5, not so good. Okay. Let's look at an example of complex dominant poles. Here was that same example we saw before. Here's the original. Here's its approximating transfer function. And here's the two step responses. Again, we think that's a fairly good match. Again, this guy's poles are at -2. This guy's at -10. It's a factor of 5 again, so a pretty good match. Here's a scary looking transfer. 4 poles, 3 zeros. We'll approximate it with first order prototype system, scaled version of the prototype system, and it's a remarkably good match. Nice. Complicated as this looks, this thing is almost the same response. Here's another one with the exact same poles, wildly off. Trick is this numerator, the zeros. You can't ignore the zeros. Let me look at those. This was the good match. Everything was along the real line. Here was the dominant pole. Everything was at least a factor of 4 to the left of the dominant pole. And even better than that, this pole and 0 tended to cancel each other out. So you had, in effect, the next nearest guy was like 8 times to the left of the dominant pole. And we got a match. On the bad match, you had zeros not only not that far left of the dominant pole, you had a complex pair to the right of the dominant pole, and in fact, on the imaginary axis. So in general, what we want for a pretty good match is all poles and zeros to be a good 4 to 5 times to the left of the dominant pole in the complex pole. We'll get into, if they're not quite that far away, if they're not 4 to 5 times to the left, how much effect do they have? We'll get into that in another video. That is the idea of dominant poles.